Hey everybody, we're going to look at the last section for this test, section 5.4, which is called differentiation of exponential functions. So first thing, what is an exponential function? We've done lots of functions that have had exponents, but that didn't make them exponential functions. For example, y equal x squared. Yeah, there's an exponent in there. The 2 is an exponent. But this is not an exponential function because the exponent doesn't have the variable in it. In other words, the exponent is just a number 2 here. Okay, so this is not considered exponential. Something that would be exponential would be, say, something like this. What if we just kind of flip this around? What if it was 2 raised to x? Okay, so now your exponent is x. X is your variable. So this is considered an exponential function. So literally, to be an exponential function, your variable has to be in the exponent. Okay, we're going to look specifically at a certain type of exponential function. What we're going to look at is exponential functions that have a base of what we call e. Okay, so what's a base? Base is simply this number that's getting raised here. So in this case, the base is 2. Okay, in the first case over here, the base is x. Okay, so again, base means the number getting raised. So we want to use the number e as our base. This is called the Euler number, spelled E-U-L-E-R. You should see a button for E on your calculator, and it's roughly 2.71828. You use it a lot in growth patterns, in calculus. In the business world, the number E is used in the calculation of continuous interest, which most banks, if you get a CD, certificate of deposit, most CDs are still calculated based on continuous interest, and this number E goes into that calculation. We're just concerned with how you take the derivative. So let's take a function, a fairly general function, y equals e raised to something with x. So y equal e to the gx. G of x is just something with x in it. So it's an exponential function. We need to come up with a formula for how to take the derivative of that. And it's going to entail a combination of implicit differentiation, which we did in section 3.3, along with logarithmic differentiation, which we did in section 5.3. Okay, so the first thing I want to try to accomplish here is get my x out of the exponent. So I need a way to get g of x down somehow. And we can do that with a rule from algebra. With logarithms in algebra, there's a rule that says exponents and coefficients are interchangeable. So if we had the log of e to the gx, we would be able to move that g of x down. Well, we can do that. It's an equation, so if we want the log on the right side, then we're also going to have to think about the log on the left side. So basically, I'm taking the log of both sides there. Okay, use that rule to move g of x down. So again, exponents and coefficients in logs are interchangeable. So I'd have g of x times the log of e. And we can actually simplify a little bit further here because you could type this in your calculator if you want. The log of e is actually 1. So really on the right side of the equation there we have g of x times 1, which is just g of x. All right, so now we have a logarithm. We want to do some derivatives. Again, in 5.3 we learned how to do the derivative of a log. The derivative of a log is a fraction. The bottom of the fraction is what you take the log of. We're taking the log of y. And the top was the derivative of the bottom. The derivative of y is 1. When we covered section 3.3, implicit differentiation, remember, anytime you do the derivative of y, you need to put dy dx behind it. On the right side, g of x is some expression with x in it, so we just do the derivative there like normal. We're using general notation here, so g prime of x can indicate that derivative on the right side. Alright, the next thing we did in 3.3, implicit differentiation, was to go through and get dy dx by itself. So to do that, I would just basically multiply each side times y. Alright, this is a pretty good rule so far, but we want to actually have it where it's completely in terms of x. It's going to make it a little bit simpler when we actually go and work derivatives. So what I want you to look at here is you have y right here. Well, at the beginning you had a y by itself on one side of an equation. Literally y equaled that. If that's true, then we can substitute that in for y at the bottom. So literally what I'm saying is we could have dy dx equal g prime of x times, instead of y was equal to e to the gx, so we can say times e to the gx. And that's literally our rule. Do you have to do this process every time? No. I'm just showing you how to get the derivative rule here. So again, if you want a more concise way to think about this, anytime I have y equal e to the gx, then the derivative is the derivative of g times e to the gx. That's the rule we need to remember. Now I want to point out a special case because it's going to look like we're not doing anything to take the derivative, and this will be the only function that exists where this happens. Suppose you had y equal just e to the x. So applying this rule above it, we need to say the derivative of the exponent. Okay, so the derivative of our exponent x would be 1, and then times whatever we had to start with. So times e to the x. Well, 1 time anything's itself, so literally the derivative is e to the x here. Okay, so this is the only function where this happens. Y is e to the x, the derivative is e to the x. That's the only function that exists where the derivative is the same as the original function. So keep that in mind when we start looking at the problems. Okay, let's take a look at Hawks. So again, this is in section 5.4. So you should see a question like this should be your first one. G of x equals 7x to the 5th minus 2e to the x. Okay, and they ask us to get the derivative. Okay, so let's do that. So I just rewritten my function here. I literally have two terms. My first term, 7x to the 5th, that's just a power rule problem. So 7 times 5 is 35, x to the 4th. My second term is where your exponential rule comes in. Okay, well we just said right here that the derivative of e to the x was e to the x. Okay, so we can use that fact here. the derivative of negative 2e to the x is going to be negative 2e to the x. So negative 2 is just a coefficient you're bringing down, and then the derivative of e to the x is e to the x. So pretty straightforward on that one. Let's put that in. 35x to the fourth minus 2e to the x. Submit. There we go. Alright, here's one that's a little bit more complicated. It's not just e to the x this time. We have 3e to the 1/4 x cubed plus 4. Okay, so if we're looking at our exponential rule, it was y equal e to the gx. Gx is basically that exponent, 1/4 x cubed plus 4. So let me write this down here. Y equal 3e to the 1/4 x cubed plus 4. Alright, so our rule tells us to get the derivative of the exponent. So the derivative of 1/4 x cubed plus 4, just think about that as its own problem for a second. The derivative of that would just be 1/4 times 3 is 3/4. Subtract 1 from the exponent, derivative of 4 would be 0. So the derivative of that's going to be 3/4 x squared. And then, again, the rest of the rule said multiply times basically what we had to begin with, right here, e to the gx. Okay, we have a coefficient here, so don't forget about that, but we're just multiplying by whatever we had to start with. You can leave it like that if you want to. I'd go ahead and multiply out. Really no reason not to. 3 times 3 is 9, so you have 9/4 x squared e to the 1/4 x cubed plus 4. So again, keep in mind, it's the derivative of the exponent times whatever we started with. That's all it is. So I'm doing a derivative here, and then I'm just bringing down the original for the second part. Okay, so 9/4 x squared e to the 1/4 x cubed plus 4. Let's go put that in. Oops. 1/4 x cubed plus 4. And let's hit submit here. There we go. Alright, so again, we had the derivative of the exponent. 1/4 times 3 was 3/4 x squared. Derivative of 4 would be 0. And then we rewrote what we had. So basically ended up with a 3/4 times a 3 to get that 9/4. Okay, this one is back to just e to the x, but the difference this time is it's not two separate terms. If you look at that, it's all being multiplied together. It's negative 7x cubed times e to the x. So we're actually going to have to do the product rule here, which we did back on test 2 or 3, section 3.1. In that section, you basically called a factor first and another factor second. So in this case, let's take negative 7x cubed, call that first. Let's take e to the x and call that second. The product rule was first times the derivative of the second plus the second times the derivative of the first. Okay, so we just basically need to plug into that mnemonic there. Okay, so first is negative 7x cubed derivative of the second, so the derivative of e to the x is e to the x, plus the second, which is e to the x, times the derivative of the first. So the derivative of negative 7x cubed would be negative 21x squared. Again, you could leave it like this if you'd like. Nothing wrong with it. I'm going to clean it up just a little bit to make it a little easier to type in. There's really no need for the parentheses on the first term here, so we can write it like that. On the second term, let's just flip it so e's at the end. So we have minus 21x squared e to the x. And that's just a cleaner way to write it, so you don't need all the parentheses and things. But again, it's product rule. First d second plus second d first. When we did d second right there, that was the derivative of e to the x, which is e to the x. So let's put this into our solution box. Negative 7x cubed e to the x minus 21x squared e to the x. There it is. Okay, we've got a bit uglier function here. Y equal negative 5 e to the 1/2 x to the 4th plus 7. And they want us to go a little bit further than just getting the derivative. Yeah, we need to get the derivative. That's what y prime is. I don't really like that notation. I prefer dy dx, but this is the notation they chose to use here. And determine the slope y prime when x is 2. Okay, so you may not have seen this notation before with the vertical line here and an x value. What this is literally the same thing as saying f prime of 2. So they're saying take the derivative and plug the number in. That's really all they're saying there. So it's a little bit new notation. You may not have seen it before, but it means the same thing as f prime of 2. Take the derivative, plug in 2. Okay, so let's get our derivative. So again, they're using y prime as derivative here. We need the derivative of our exponent. So 1/2 times 4 is 2. That's going to be x cubed. Derivative of 7 is 0, so that's gone. And then we multiply times what we had, which was negative 5e to the 1/2 x to the 4th plus 7. Let's go ahead and multiply that out. 2 times negative 5 is negative 10. That's x cubed e to the 1/2 x to the 4th plus 7. Okay, so that's the derivative like we did in the other problems. We're just going to do one extra thing, and that's go back and plug in this x value they ask about. So y prime when x is 2, that just means plug 2 in for x. And you could type all that in just like that if you wanted to. I'm going to try to clean up just a little bit here, just to make it look nicer. See, so 2 cubes 8 times negative 10 is going to be negative 80. Then we're going to have e raised to 2 to the 4th, which is what, 16 times 1/2. So that's going to be 8 plus 7 is going to be 15. Do yourself a favor and leave it in that form. For one reason, Hawks will not let you put a decimal answer on this question. The reason being the value is so big. If you just plug that into a calculator, negative 80 e to the 15th, actually my calculator will handle that one, but if the exponent was just a little bit bigger, you'd probably get some some weird thing on the screen of your calculator where it's some number point something something something, and it's going to have a weird E sign with an exponent on it, and that's going to tell you to move the decimal places, a certain number of places to the left or right. In other words, it's going to be a real big value. If this was e raised to a negative exponent, then you'd have a really, really small value, almost close to 0. But either way, suggestion is just go ahead and leave it in exact form. And so I'm going to just type this in, negative 80e to the 15. There we go. Alright, that's basically a repeat of the first question we saw. We've done one like that. Okay, there we go. So this is a pretty short section. Just taking derivatives as exponentials. And again, that rule is take the derivative of the exponent and then rewrite whatever you had. That's all there is to it. Good luck.